So we're going to start off this week by looking at 7.5. Okay, when we left off in 7.4, we were talking about different kinds of identities. So we have broke them down into different categories. We had reciprocal. Okay, we use those all the time. Like if you're going to type in secant or cosecant in the calculator, we have to flip, do 1 over. We also had the Pythagorean identities. One of them is sine squared plus cosine squared equals 1. Do people remember that one? Okay, so we talked about those different identities. Well, what we're going to look at today are 6 different identities. 2 for sine, 2 for cosine, 2 for tangent. And they're called the sum and difference identities. So the idea here is if you have a plus or a minus inside your argument, you don't want a plus or a minus. So how do we get rid of it? Well, the first question is, could we just do that? Well, let's think about it. When you add 3 inside the argument, what kind of transformation would that be? The plus 3 would do what? Yeah? This would shift it left 3. So this thing is a shift left 3. Now, what happens when you add something on the end of the function? What kind of transformation is that? Yeah, Jack?
Vertical shift.
That's a vertical shift. So these aren't even the same thing just based on thinking about transformations. This is a shift left. This one on the over here is a shift up. And it's not even a shift up 3. It's a shift up sine 3. So the point is, these two things are not the same. You can't distribute the word sine like this was a number in the front and use the distributive property. That doesn't work. So then how do we get rid of a plus or a minus inside the parentheses? Well, that's what I'm going to try to show you. This is what we call a sine sum formula that you need to use. We're not going to start by looking at sine of a sum. I'm going to start you off with what's called the cosine difference formula. And the cosine difference formula is used when you have cosine and you have subtraction inside the argument. And that's the formula. The proof of that formula, that's a little bit much to kind of go through. So we're going to skip the proof. We will prove some of these other ones, like the cosine of a sum. We'll prove that one. But we can prove that pretty easy based on knowing this one. It's just this one is a little time consuming to prove. All right, now what does the formula say? Well, you have cosine of alpha minus beta. I'm going to refer to alpha as angle 1. I'll refer to beta as angle 2. So 1, 2. So it's cosine of my first angle times cosine of my second angle plus sine of my first angle, sine of my second angle. A couple of patterns you can kind of notice here. In this particular formula, the cosine functions are grouped and the sine functions are grouped. What do I mean by grouped? I mean they're together. The cosines are in the left part, the sines are grouped on the right part. Whatever symbol you put here, it's the opposite here for this formula. And then the angles that you plug into your cosine and sine functions, the first angle, the second angle, the first angle, the second angle. 1, 2, 1, 2, right in order. So that's called the cosine difference identity. Again, we're not going to go through the proof. So we've talked about unit circle trig in the past, and we talked about certain angles that were multiples of 30 and 45. So if you look at the unit circle trig diagram, all the angles that we've done before are labeled, the multiples of 30 and 45. But if you notice, when you label the 30s and 45s, they're not equally spaced. Okay, you're missing. There's like a gap, right? There's a gap here, another gap here, And there's two gaps like that in every quadrant. And we've never done these angles before. What do you think this first green dot is? What angle? Yeah? 15. These other ones are multiples of 15 that we didn't get to. So you've got a 15, a 75, 105, 165. If I make a mistake, just let me know. 195. This is 255, 285, and 345. So all those ones in green are ones that, with what we're learning today, we're going to be able to do them. Now, if we don't remember certain things about the unit circle, this is going to be a little tricky. So let's just go over a couple decimals that are important that are going to come up when we do some problems. Root 2 over 2 was a number that came up a lot when we did unit circle trig. If you remember, it had to do with a 45, 45, 90 triangle, root 2 over 2. And if you change that to a decimal, you get about 0.707. So, if we do a problem today, and we type it in on the calculator, and we get 0.707, and it keeps going, we need to write that as square root 2 over 2. So we got to remember 0.707 turns into that. Okay, another one that's going to come up, if you're dealing with a 30, 60, 90 right triangle, root 3 over 2. That was a number that came up a lot in that triangle. In fact, if I bring this up, maybe if I scroll down, they might label some of the coordinates somewhere that we studied. Well, I don't know if you can see that one, but there's the root 2 over 2. And that one has to do with a 45-degree angle. Root 3 over 2, there we go, there's all the coordinates. So root 2 over 2 has to do with your 45. Root 3 over 2 has to do with 30s and 60s. Okay? So we need to know that root 3 over 2 is 0.866. That'll help us if we don't remember this whole diagram. So this is what's going to come up when we deal with sines and cosines. And when we deal with tangents, there's a couple other numbers that will come up. Let's go back to this chart. Actually, we don't need the chart. When you deal with tangents, you might see square root of 3 pop up. And that's about 1.73. And another one you might see pop up is root 3 over 3, which is 0.577. Yeah. All right, so those are some special decimals that we're going to see, that when we see them, you need to change it to the fraction that I put it's equal to. Any questions on those special decimals? Okay. So let's go back here. And let's see if we can find something about this 15. Let's do the cosine of it, okay, since we're talking specifically right now about the cosine difference formula. The way you figure out the cosine of 15 is you have to split up the 15 degrees. The way we're going to split it up is as a difference. And you have to pick two things, but you can't just pick any two things. Like you can't do 16 minus 1. That wouldn't be helpful. The two numbers that you pick that are going to go here and here have to be multiples of 30 and 45. So can anybody think of two numbers that we can subtract that are multiples of 30 and 45 that give us 15? Yeah?
45 and 30?
Yeah, 45 minus 30. You don't even have to do anything super fancy, but if you get stuck, it might be helpful to look at a diagram like this and start looking at some of these numbers. Not the ones I wrote in green, the ones that were already there. okay, and see if you can come up with a way to get the number you want using the numbers that I've circled in red. And in this case, Eli did it perfect, 45 minus 30. It's the simplest thing you can use. Now, we're going to use the cosine difference identity to break this down. In our case, alpha is 45 and beta is 30. So fill in a 45 and a 30 everywhere you see alpha, beta. So let's look at the pattern. Cosine, cosine, plus sine, sine. What I usually do is just write that down first. Cosine, cosine, sine, sine, and what goes between them again? A plus or a minus? Yep.
Plus.
Plus. And now fill in all your angles. Alpha, beta, alpha, beta. So it's going to be 45, 30, 45, 30. Okay. Any question on setting that up? So now we're going to go through all four of those and write down what each one of them comes out to. Let's start with, well, you know what? Let me type them all in so we have them already. And then we don't have to go back and forth on the calculator. So first of all, I'm in degrees. Make sure my calculator is in degrees. Cosine 45. Cosine 30. Sine 45. And sine of 30. Okay, let's go through and write each of those down. All right, so what is the cosine of 45 written as an exact fraction? So you want to recognize that decimal. Yeah?
Square root of 2 over 2.
That's your square root of 2 over 2. And if you ever forget, you could check. Take the square root of 2, divide by 2, and you get 0.707106. That's the same thing. How about cosine of 30? What does that one come out to? Yeah.
Square root of 3 over 2.
Yep, that's your square root of 3 over 2. Plus, what's the sine of 45? Yep, go ahead.
Square root of 2 over 2.
Square root of 2 over 2 again. Times the sine of 30. Well, this is 0.5. We'll write it as 1/2. Okay, now for the final answer, we just multiply this and add it up. So these two can be multiplied together. So we'll do those, and then we'll do those. So when you multiply fractions, you just go straight across. Square root of 2 times square root of 3 is square root of 6. 2 times 2 is 4. And I'll do the other one. Square root of 2 times 1. And then the bottom is 2 times 2 is 4. And since they have a common denominator, you don't need to keep them as separate fractions. You should always take things that have common denominators and put them together. Square root of 6 plus square root of 2 over 4. And that's the exact answer for the cosine of 15. Very easy to check that that's right. Let's type in cosine 15. Cosine 15. All right, you get 0.9659. Now, let's type in what we got and see if it comes out the same. Square root of 6 plus square root of 2 sorry, I messed that up. Square root of 2. And we're going to divide by 4. Right? And you can can see cosine of 15 and what we got, it's exactly the same thing. So we know we did it right. So on the test or in the homework, if they ask for an exact answer, you're looking to write something like this. It's going to have square roots. Don't put 0.9659. That's not exact. Okay. Questions on that one? So this doesn't allow us to do every single angle you could think of, because like, could you do 10? Like cosine of 10? Not really. Because you need a way to write 10 as a difference of 30s and 45s, and I don't think you're going to be able to do that. But you can do the 15s. All right, let's try this one. So this is a verify. That means the answer here is not numeric. Remember, when we do a verify problem, you always start with the side that looks more complicated, and you work with that and try to simplify it. Which side looks a little bit more complicated here? The left or the right? Either? Yeah, so we're going to work with the left-hand side. And let's look at the left-hand side. What trig function do you see on the left-hand side? Okay.
Cosine.
Yep, cosine. And what operation do you see inside the parentheses? Francesca?
Subtraction.
Subtraction. So this is a cosine difference problem. You need to look up the identity for the cosine of a difference. So we have that right here. Cosine difference formula. Cosine, cosine, plus sine, sine. So cosine, I'll just write the formula first. Cosine, sine, sine. And Abigail, what am I going to fill in my first parenthesis? Pi over 2. Jack, what am I going to fill in the second one?
Pi over 2.
No.
I'm lost.
All right, let's go back and look at our identity. What do we have in the place of alpha in our problem? Pi over 2. What do we have in the place of beta in our problem? Yep, and what letter? Yeah. Theta. So in place of alpha, we have a pi over 2, and in place of beta, we plugged in another Greek letter, theta. So that's the identity. So do you see what's going to go here now?
Theta.
Yep, I'm going to put theta. And then repeat that. So now fill in again, alpha and beta. Pi over 2, theta. Now, look at the two cosines. One of these we can simplify, one of them has to stay the same. Which one of those cosines could I plug in and simplify it? Yeah.
Alpha.
Well, I see a pi over 2 and I see a theta. So it's one of those two.
Beta.
Which one?
Beta. I said alpha first.
Well, there's no alpha here. We have a pi over 2.
Oh, the pi over 2.
Yeah, the pi over 2. So we can simplify the cosine pi over 2 because that's numeric. Theta is a variable. You can't do anything with that. So pi over 2. What's pi over 2 in degrees? I don't feel like changing my calculator into radians to do it. Yeah.
Isn't it 30?
That's pi over 6. Okay?
Isn't it 90?
90, yeah. So remember, pi is 180. So pi over 2 is 90. So I'm going to take the cosine of 90. If you don't want to figure that out, then change your calculator to radians and then do it that way. So the cosine of 90 is 0. So this cosine of 90 is 0 times cosine plus, now let's see what the sine of 90 is. Sine of 90 is 1. So this turns into 1. Hey, Casey, what's going to happen at this step? Do you see what's going to happen, Casey? Well, what's going to happen with this first part? It's 0, right? This first part is 0 times cosine. So this first part basically just disappears. Anytime you multiply something by 0, it's gone. What's going to happen with the second part? Let's see what I'm going to get there. Oh, Tyler?
Just gonna get the sine of theta?
You're just going to get the sine of theta because it's just sine of theta times 1. So that doesn't do anything. So it's just sine theta. So we're done. And now we just scroll back up and see, is that what they wanted us to get on the right-hand side? Yes, it is. So we turn the left-hand side into the right-hand side using the Sine Difference Identity. Questions on that? So it's a proof, kind of like some of the proofs we did last week, but I think it's a little easier because you have to use the identity, and it pretty much guides you through. You don't really have any choices. Like, should I change the sines and cosines? Should I? You don't really have any of those choices. All right, let's try this one. The cosine of pi minus theta equals negative cosine theta. All right. So we're going to start with a cosine difference on the left-hand side. Can someone remind me, how does the cosine difference formula start out? Eli?
It starts out with cosine alpha minus beta.
All right, so we'll do cosine.
Or,
and
the right part is cosine alpha, then cosine beta.
All right, so yeah, cosine, cosine. All right, and Zach, what comes after those?
Plus sine,
Yep.
sine.
Plus sine, sine. Perfect. So we've got the equation kind of set up. Now we fill it in. Ashley, what's going to go here?
Pi.
Pi, and here
Theta.
theta, and then repeat it again. Pi and theta. So let's simplify what we can. The cosine theta and the sine theta, those are going to stay right where they are. But let's do the cosine of pi. Again, I just don't feel like switching to radians. So what's pi? Yep.
180.
180. If you want to switch to radians, it's fine. Just change the mode. So cosine of 180 is negative 1. So we have negative 1 times cosine. And now we're going to do sine of 180. That's 0. 0 times sine. And what's going to happen at that step? Yeah.
You're going to get negative cosine of theta plus
Yeah.
0.
Yeah, this is just plus 0, so we don't need that. And this is negative 1 times cosine, which is negative cosine. Now we scroll back up and we see, is that what they said we should get? Yes, it is. Okay, any questions on that? So you'll have two very similar to that on the test. And we're going to use this one again in a little bit. Because right now we know how to do cosine of a difference. Well, this formula gives you a way to turn cosine into sine. So if we can turn cosine into sine, then we can maybe do sine of a difference or sine of a sum. But this is the formula that will help us figure that out. So we're going to come back to this in a little bit. All right, so we did cosine of a difference. Let's see if we can figure out how to do cosine of a sum. A couple things are going to come up, and I just want to show you them on the calculator first. Let me graph cosine, and I want you to describe the symmetry that you see. Does anybody see how you could reflect that graph? And it would look exactly the same. Yeah.
Across the y-axis.
Yep. If you reflected it across the y-axis, if you did a horizontal reflection, the graph would look exactly the same because the y-axis is a line of symmetry. So that means if I wanted to reflect it across the y-axis, I would do that. You put a negative inside parentheses. That's a horizontal reflection. And notice if I put the negative there, it's tracing right over it because it's exactly the same. You can see it, well, it was right in the middle of tracing over it. So that means this. If you do a reflection of cosine, you get the same thing as the original. Now, let's look at sine. And let's see if that same idea works. All right, let's take sine. And does the graph of sine have symmetry over the y-axis? What do we think? Is the graph of sine symmetric over the y-axis? Bailey, what do you think?
Yeah.
Okay, let's take a section and actually flip it. If you took that and you flipped it over the y-axis, where would it end up?
It's the second quadrant.
Yeah, it would end up in the second quadrant. It would end up right here, right? That's what you would get if you flipped it. Did that land on top of what was already there? No. So the graph of sine doesn't have symmetry over the y-axis. So if you reflect it, it would end up there. But then if you reflected it again vertically, it would end up here. So there is a symmetry, but the way you would have to do this one is if you wanted to reflect it horizontally, that would be the same as reflecting it vertically. And I can show you that as a picture. So here's y1 is going to be what happens if you reflect horizontally. y2 is going to be what happens if you reflect vertically. There's a horizontal flip. There's a vertical flip. It's exactly the same thing. So a little bit different than cosine, but basically what's happening each time is it gives you a way to get rid of a negative inside the argument. with a cosine, you can just get rid of it completely. Doesn't matter. With sine, you can't get rid of it, but what you can do is put it in front as multiplication. This is like putting a times 1 in front of it. So you can think of it like this. -1 times sine. Same thing as negative sine. Any question on those two? All right, so now let's see if we can figure out this. Cosine of a sum. Well, the only formula we know right now is cosine of a difference. So we're going to have to use that somehow to get this. Does anybody see how you could take this and rewrite it as something minus something? And it would be the same as what's right there. How can you rewrite addition as subtraction? Yep.
I could do alpha minus negative beta.
Yep. You could do alpha minus negative beta. Perfect. Now we rewrote addition as subtraction. There's my first angle. There's my second angle. So I have two things that I'm subtracting separated by a minus sign. It's exactly the same as what we had right here. Subtracting two things separated by a minus sign. Okay, so let's apply our formula to this and see what happens. Okay, Jake, can you remind me how the cosine difference formula starts out?
Cosine times cosine.
Cosine times cosine, yep.
Plus sine times
Sine times sine. And Sarah, what's going to go in the first parenthesis? Alpha. And the second one? Negative beta. We have to deal with that negative inside there, but we have a way to deal with the negative in a second. Alpha, negative beta. Okay, let's start with the negative inside the cosine. What can you do with that negative right there? Yeah.
Put the negative to the outside. Oh wait, just remove the negative.
Just remove it, yeah. When you have cosine, you can just remove it. So this negative doesn't make a difference at all. Now, what about this negative right there? What can I do with that negative that's inside the sine function next to beta? Yeah?
You pull it out and put it in front of the side.
Right, we can put that out in front as a times -1. When you multiply something by -1, it makes it the opposite. So this negative is really going to turn that into a minus. And that's the formula for cosine of a sum. Cosine, cosine, sine, sine, just like when we did it the first time. But what's the one thing that's different for the cosine sum formula compared to cosine difference? There's only one thing that's different.
It's not a negative anymore.
It's what?
It's not a negative anymore, it's a positive.
Well, it's a negative now, right?
Yeah.
So this time it's a negative, and when we did it the first time, it was positive. That's the only thing that changed. So, pretty easy formula, because it's so similar to the last one. Okay, so again, cosine sum formula. So now, we could figure out something like this. Cosine 75. There are many ways to do it, but I want to think of this as a sum. Let's go back to this chart. And can somebody see how I can get 75 as a sum of the numbers that are circled in red. You have to use one of those 12 numbers. Well, two of them. Yeah.
45 plus 30.
Yep, you can do 45 plus 30. Now, does anybody see how you could do it as a difference? There are two numbers up there that if you subtract them, they do come out to 75. Actually, there's more than one way to do it. Yeah, Jack?
No, I think that's good.
You have to use the ones that are circled in red. Yeah, you gotta stick with those. Because 15 isn't one that we would know off the top of our head nicely. It's not going to be one of those nice decimals. Yeah.
135 minus 60.
You can do 135 minus 60, and that'll give you 75. Or you could do 120 minus 45. That would also work. So, if on the test it asks you to figure out cosine of 75 and it doesn't say how to do it, you can do it any of those ways. I'm just doing it as a sum because we haven't practiced a sum yet. 45 plus 30. All right, so Abigail, can you just tell me my formula first before I fill it in?
Cosine 75.
Yeah, you don't even have to fill it in yet.
Cosine alpha minus beta equals cosine alpha times cosine beta.
And what comes after this?
I'm not sure.
So let's go back to our cosine sum formula. So what I'm asking for is for you to tell me this. But you don't have to fill anything in for the arguments. So it's cosine, cosine, minus sine, sine. That's the pattern. Cosine, cosine, minus sine, sine. We'll go back after and fill in angle, angle, and then the other angle and the other angle. All right, so we've got cosine, cosine, minus sine, sine. And Casey, what am I going to fill in here?
45.
Yep, 45. And Eli right here,
30.
30. And do it again. 45, 30. Okay, now we have to go through each one of those, but we've already done every one of these. We did 45s and 30s in the first problem. Does anyone remember what cosine of 45 is? Yeah?
Square root of 2 over 2.
So root 2 over 2. How about the cosine of 30? What was that one? Yep, Eli?
Square root 3 over 2.
Square root of 3 over 2. How about the sine of 45? Jack?
Square root 2 over 2.
Good. Square root of 2 over 2. And the sine of 30 is 1/2. Okay, so let's multiply that all together and write our denominator. Francesca, what's going to be my denominator? In both parts.
Oh. 2? No.
So when you multiply these together, you wouldn't have a denominator of 2. Four, right? It's going to be just like when we did the sine of 15 or whatever one we did, cosine 15. It's going to be almost the same thing. So denominator of 4. And Tyler, what's the square root of 2 times the square root of 3?
Would it be the square root of 6?
Yep, square root of 6. And Zach, the square root of 2 times 1?
Square root of 2.
Just the square root of 2. And that's your final answer. Square root of 6 minus square root of 2 over 4. I think the only difference when we did the first problem, I think that was a plus sign. So these kinds of problems, they end up with lots of square root of 6s, square root of 2s, and 4s. The only thing that ends up changing is sometimes you have a plus up here, sometimes you have a minus, sometimes you have two minuses. Just depends on the problem. Okay, any question on that? That's the exact answer for the cosine of 75. All right, so let's see if we can figure out the sine sum formula. Okay, so now we're looking at the sine of a sum, and we're going to do sine of a difference. Difference, I'm just going to give you the formula, because it's very similar to doing the sum. Now, we know this already. How do we know this? We proved this. This was a problem we proved, and I said we'll come back to it. Sine theta equals cosine pi over 2 minus theta. Let's go back to our example. Right here. Sine theta equals cosine pi over 2 minus theta. So we proved this in example 2a. We didn't know that before we did that, but now we do. Okay, so we proved it. So keep this in mind, and this is going to pop up somehow in a second. All right, so I want to see if I can figure out the sine of alpha plus beta. Well, what I'm going to do is I'm going to substitute this right here. And the reason I'm going to substitute that in for that box is this formula gives me a way to turn a sine problem into a cosine problem. Why would I want to turn it into a cosine problem? Because I already know all the formulas for doing a cosine problem. So that's going to help me figure out this one. So I'm going to have cosine of, and you're going to, everywhere you see a theta, I want you to replace it with what we're trying to figure out. Alpha plus beta. Anything else stays right where it is. Just replace the variable with what we're plugging in. So pi over 2 minus alpha plus beta. And you do need parentheses around that alpha plus beta because you're subtracting all of theta. And we're replacing all of theta with this. So you're subtracting that whole thing. Okay, so any question on the first one? Now, what do I have to do with this minus in front of the parentheses? This is why I put the parentheses there. Yeah?
Distribute it.
I have to distribute it. So it's cosine pi over 2 minus alpha minus beta. Now, I'm going to put boxes around this to hopefully kind of make it make sense. That's box 1. That's box 2. Look what we have right there. Cosine of a difference. This is box 1. This is box 2. It's just like this formula. That's box 1. That's box 2. So now, use your cosine of a difference formula. Everywhere you see box 1, fill in what we have for box 1. Everywhere you see a box 2, fill in what we have for box 2. And see what happens. All right, so we start out with cosine, cosine, sine, sine, and what goes in the middle when you have a cosine difference problem? Yeah?
An addition sign.
An addition sign. And now fill in your angles. 1, 2, 1, 2. So we have, this is 1, this is 2, this is 1, and that's 2. And now, let's look at what ends up happening. You can't do much with this. And what would you do with that? It's just a single trig function. There's only a single thing in the parentheses. So that won't simplify. Neither will this. But look at this. Cosine of pi over 2 minus alpha. Or cosine of pi over 2 minus an angle. What does the cosine of pi over 2 minus an angle equal? Yep.
Sine theta.
Sine of your angle. Anytime you write cosine of pi over 2 minus an angle, it just turns into the sine of your angle. So in this case, sine alpha. Now, this one we didn't prove, but maybe you can take a guess what happens. What do you think sine pi over 2 minus an angle turns into? Very similar to what happened here. Yeah?
Negative sine of alpha.
It doesn't turn into negative sine of alpha. So when you do pi over 2 minus alpha, what ends up happening is this trig function changes. So it turned into sine of the angle. So what do you think this one would turn into? Yeah?
It'd be negative cosine.
Just positive.
Oh.
Yeah, so it's going to turn into cosine of the angle. We proved this. I could prove this one just as easily. Okay, but we just didn't go through it. And there's your formula for the sine of a sum. Okay, so look at the difference here compared to cosine formulas. Does anybody notice something that's different when you compare this to the cosine identities we just did? Yep.
Sine is on both sides and so is cosine.
Yep, they're mixed. You don't have cosines on one side and sines on the other, they're mixed. Sine, cosine, cosine, sine. The angle still goes 1, 2, 1, 2. You can still do that. The other thing that's different, you had a plus sign inside the parentheses. You have a plus sign when you expand it out. The symbol in the parentheses stays the same this time. You don't make it the opposite. So I asked earlier what the difference was between the cosine sum and cosine difference, right? And it was pointed out there was only one thing that was different. Well, there's only one thing that's going to be different here when you compare the sine difference formula to the sine sum formula. Anyone have a guess what the one thing that will be different is going to be? Yeah?
It turns to minus then.
Yep, this is going to change to a minus. When it's the sine of a sum, you do a sum. When it's the sine of a difference, you do a difference. But it's still mixed. Just like Zach had mentioned, it's still sines on both parts of it. Sine, cosine, cosine, sine. It gets a little tricky to remember all the different formulas, but that's why you can make a reference sheet, so that'll help. And this allows us to do the same kind of problems that we've been doing before. We could do the sine of 15. Let's try one. Let's make one up. Let's do, let me go back to that diagram and let's pick a number off that. All right, so Ethan, you pick a number that's in green. Which one do you want to do, besides 15 and 75?
197.
195? Okay. And do you want to do sum or difference?
Sum.
You want to do a sum. Okay. So we're going to see if we can try to write 195 as a sum of two numbers. Sine 195. And can anybody see how to write that as a sum of two numbers? And you have to use numbers that are circled in red. Okay, you want to get 195. I think I have one way to do it. Yeah?
135 plus 60.
Okay, 135 plus 60, that'll work. That's not the way I was thinking of. I was thinking of 150 plus 45. But you can definitely do 135 plus 60. It'll come out the same. Yeah. Let's do 135 plus 60. And you could have done this as a difference. Okay, that's why I let him pick sum or difference. It wouldn't have mattered. All right, so 135 plus 60. And how about Jake? Can you just start me off with the pattern? You don't have to even fill anything in. Just the pattern of my formula.
Sine, cosine.
Yep.
We're doing a sum and difference. Oh, plus cosine.
Perfect. Sine, cosine plus cosine, sine. Now fill in 135 and 60. Now, these might not be angles we've dealt with before, but the decimals are going to be all the same. You're going to get the 0.866s and the 0.707s and the 1/2s. Same numbers. Okay, let's go through it. I'll type them all in just so we have them all ready to go. Sine 135, cosine 60, cosine 135, and sine 60. All right, let's convert all those to the fractions. All right, let's start with sine 135. What's that one? Jeff?
Square root of 2.
Yep. Square root of 2 over 2. How about cosine of 60? You guys are thinking too hard about that one. Yeah?
Is it square root of 3 over 2? Or square root of 3? Or none of the above?
None of those choices. But it is up there. Yep.
1/2.
1/2. Cosine 60, 0.5. How about cosine 135? Yeah, Ethan?
Negative square root of 2 over 2.
That's the negative square root of 2 over 2. Yep. And the last one, how about cosine sine of 60? Yep.
Square root of 3 over 2.
Square root of 3 over 2. Okay, so same type of problem. You're going to get root 6s, root 2s over 4. Just a variation on the numerator being positives and negatives. Bless you. Square root of 2. Now, that's going to be a minus, because that square root of 2 times square root of 3, that's square root of 6, but you're subtracting, because it's a minus. And the denominator will be, yeah, Sarah? 4. There you go. So that's the exact answer for the sine of 195. If you're not getting decimals like this when you do a sine and cosine problem, then you didn't split it up into multiples of 30 and 45. Questions on that one? All right, so you guys got the sine, sum, and difference formulas. Last thing we're going to look at And this is gonna kind of lead us into what we do tomorrow, so we're not gonna look at all of this today, is this one. We've looked at how to deal with having a plus or a minus inside the argument. Well, another problem we can have that comes up a lot is a 2. You don't want anything in the argument. All you want is the letter. You don't want a plus, you don't want a minus, you don't want a 2. So how do we get rid of this 2? Well, it's not as easy as just doing something like this. Like you can get rid of a 2 by dividing by 2. You can't do that here because this 2 is inside the sine function. So you can't just move it in front. You can't. That doesn't work. Right? So what can we do? Well, let's see what we can do. What's another way to think of 2x? If you had to explain that to somebody that doesn't understand what it means to put a number in front of a letter. How could you write that a different way? And I don't mean x times 2. That's the same thing. Yeah?
X plus X.
Yeah, you could do x plus x. Now, look at what we have. That's a sine. That's a sum. This is the sine sum identity. So let's do the sine sum identity on it and see what happens. That's how we can figure it out. Can somebody just start me off again with the template, and then I'll fill my angles in after. Tyler, can you tell me what the formula is?
So just cosine. Cosine plus sine sine.
That's when you have a cosine, one of the cosine identities. This one's a sine identity. Sine sum, Ashley?
It would be sine of universe, cosine of universe plus cosine plus sine.
Yep. So sine, cosine, sine.
Yep.
And you're putting a plus between them. And what are we going to fill in for my first argument? Yep.
X.
Second argument?
X.
X. So x, it's actually the same thing. Now, think of it like this. When you multiply two things together, and that's what we're doing here, cosine times sine, does it make a difference the order you multiply them? No. It's 5 times 6, 6 times 5. It doesn't matter. So let's just switch that order. Because I want you to notice something. What do you notice about this term and that term? Yeah.
They're the exact same.
They're the exact same thing. So how many of them do we have?
2.
2 of them. So this equals 2 of the sine, cosine terms. And that is the formula for getting rid of a 2 inside the sine function. Sine 2x turns into 2 sine cosine. Let's graph it and see what that looks like. Okay, so here's sine 2x, and here's 2 sine cosine. When I get graph, what am I expecting to happen? Yeah, Eli?
They don't overlap, or they do?
Well, what does all this stuff say?
They do.
They do. It says sine 2x equals 2 sine cosine. So they should be exactly the same graph. There's sine 2x, and there's 2 sine cosine. I think it's drawing it a little slower, maybe. But they are the same thing. Okay, any question on that? So this particular formula, this is called a double angle identity. Specifically, this is the double angle identity for sine. Tomorrow, we'll look at the double angle identity for cosine, and we might look at a double angle identity for tangent. So everything there, let me just check 17 and see if you can do that one. That is a double angle identity. But if it involves cosine, I haven't tidied that yet. Nope, it only involves sine. So that will be the homework for tonight. Tomorrow we'll continue looking at 7.5 and start off with double angle identities.